start the fourth lecture of stochastic process. So today we'll cover concepts on convergence of random variables. And some limit theorems. Limit theorems being the um, law of large numbers and central limit theorem. So before going and seeing convergence of random variables, we'll just see what convergence of real numbers means. So first we'll see convergence of real numbers. Okay. So first I'll give the definition. So in this definition, what I'm trying to say is you have a sequence, infinite sequence of real numbers. What does it mean when you say that the limit of the sequence is some number x? So let you have a sequence xn, n belongs to n. So basically, yeah, for xn belongs to r. Um, then we say that limit n tends to infinity, xn equal to x. So this concept notion of limit, like the sequence converges to a point x, is said that there exists n naught belongs to the natural numbers for all epsilon greater than 0, such that the distance between xn and x is less than epsilon for all n greater than or equal to n naught. Okay, so what does this mean is, so suppose you have an infinite sequence of real numbers. Now you want to know where does that infinite sequence of real numbers converge to. So this convergence you can check by checking that if there exists one number after that number. So what you do is first you pick an epsilon which is greater than 0. So you give me an epsilon which is greater than 0. Once I know that epsilon, I'll give you a number, a natural number, which is a function of epsilon. This is implicitly stated. It's not given. So you give me epsilon, I'll give you an n naught such that the distance between all the numbers after n naught is less than epsilon. If this happens for all the epsilons that you can give me, then we say that the limit xn is equal to x. Okay, so we'll use this later. This modulus, what this says is xn minus epsilon is less than x is less than xn plus epsilon. I hope that is clear. So this whole inequality says that x, the limit of the sequence, lies in plus epsilon minus epsilon distance. So xn lies in plus epsilon minus epsilon distance of x. That is what this is. Okay. Okay, I think I got this wrong. This is x minus epsilon, x minus epsilon, xn, x plus epsilon. Yeah, so xn lies between plus minus epsilon of x at all times. Okay, so this was convergence. Now, how can you say something diverges? So how can you say that something diverges? So suppose you have sequence xn. Xn, I say that it converges to plus infinity. So for any m greater than 0, there exists n naught belongs to natural numbers such that for all n greater than or equal to n naught implies xn is greater than m. So now this n naught is a function of m. This is implicitly stated. So when I say that xn diverges off to plus infinity, that means the sequence diverges off to plus infinity. What does it mean? That you give me any number, I'll give you a natural number such that for all the indexed sequences in xn, it will be greater than this number. If it is greater than that number for any m that you can provide me, the sequence will eventually terminate at plus infinity. That is what this means. I'll give examples and we'll go through this. So one example you can see is, okay, so the series of natural numbers. So this, if I have a sequence of natural numbers, so if the sequence are x1 equal to 1, x2 equal to x3 equal to 3, x4 equal to 4, so basically you have xn equal to n. Then you give me any number plus 1, that number, you'll always find that uh, any index number greater than that number is always greater than the number that you have given me. So the limit of this goes to plus infinity. Similarly, you can write xn, a sequence goes to minus infinity for any m greater than 0. There exists n naught such that x greater than or equal to, sorry, n greater than or equal to n naught implies xn is less than minus m. So similarly, in the positive, when you are saying that xn converges to plus infinity or xn diverges towards plus infinity, what you're saying is there exists a positive number after which all the elements in the sequence will be greater than that number. Similarly, for negative infinity, there exists a negative number minus m, where m is positive, such that after some time, all the elements in the sequence will be less than that negative number. Then you can say that it converges to minus infinity. There are sequences which doesn't diverge off to plus infinity or minus infinity, or either converge. They keep on oscillating. So suppose you have a sequence where you have xn equal to minus 1 whole power n. So this sequence doesn't converge. It doesn't diverge off to plus infinity, doesn't diverge off to minus infinity. It keeps on oscillating between plus 1 and minus 1. Okay. I hope that is clear. So I'll just draw a small graph of what convergence actually means. So suppose this is your real number, right? You have, so you have a sequence whose limit is x. This is your x, this is your limit. So you have limit n tends to infinity, xn equal to x. Now you have x1, x2, x3, which keep reaching uh, x. And then after some point, you have, sometimes it may exceed, it may come back, but it gets closer and closer to x. So uh, to show that something converges to x, what you actually do is, so pick an epsilon which is greater than 0. This could be any epsilon. Once you pick an epsilon, try to find an n naught. So n naught here is the index such that, so once I pick epsilon, what I have is, this is x. So I have x minus epsilon, x plus epsilon. Try to find an n naught such that all the numbers, so x n naught plus 1, x n naught plus 2, and so on till infinity, lies in this region. If that lies in this region, then you have done one part of it. So you need to do this until for all epsilon greater than 0, you can show that it lies between any epsilon that you pick which is greater than 0. Then you can say that the real number sequence converges. So yeah, I hope you have seen many of these type of convergence, 1 by n convergence, 1 by n square convergence. I'll not go into this too much. So what I'll be taking from this is, I want a similar notion of convergence for random variables, not for real numbers. So, but before that, what we see is, okay, so now we are going to convergence of random variables. So random variables are actually functions. They are not a sequence of real numbers, but random variables are basically deterministic functions. So once an outcome happens, you know what that random variable will map to which number. So we'll always start with probability triplet, the probability space. You have an outcome space, you have an event space, you have a probability measure. On this probability space, you are given a sequence of random variables. Now, this sequence of random variables could be anything. Each random variable could be a function of n, could be IID, could not be IID. It doesn't matter. We are not going into that, but you're just given a sequence of random variables, real valued random variables. So the first definition that we'll cover today is, so there are many notions of convergence in random variables because uh, so, uh, some notion of convergence is very strong convergence, some notion of convergence are very weak convergence. So depending on what kind of stuff you want to prove, we have different notions of convergence in random variables. So what does notion mean is that um, so if the sequence of random variables satisfies some property, then we say that it converges uh, for this property. Now, for this property, for that property, intuitively we have given names. There are five notions of convergence in random variable. We will go through each of them one by one. So first one is pointwise convergence. This is also known as sure convergence. Uh, so in point-one convergence, first you have a sequence of random variables. So we say that uh, limit, sorry, limit n tends to infinity. Okay, I'll write down the notion. So we say that xn converges pointwise to x. So this is basically saying that the limit of this with the property satisfies the pointwise property and converges to x. If it converges to x, what does it mean is for all omega belongs to. So you know that random variable is basically you take the outcome and it maps to a real number. So what you do is you take all the outcomes one by one, collect all the outcomes one by one, and see that for all the outcomes, does it converge to the random variable x? If it converges to the random variable x, then we say that x, this sequence pointwise converges to x. So what you do is you first fix x. When you fix x, all you get, see, fix omega. When you fix omega, all these terms are just a deterministic sequence of real numbers. And you check whether this sequence satisfies this real number convergence of real numbers criteria to this number. If it is true for all omegas that are in the outcomes output space, then you can just say that xn converges to x pointwise. So the important thing here is xn is just a sequence of real numbers. And then check the definition on the. I'll give some examples. I'll state all the convergence and I'll give some examples. Okay, so next definition is almost sure convergence. So basically the pointwise convergence is you don't have any rule. You want the sequence of random variables to converge to a random variable x for all outcomes. You don't care whether that outcome is high probability or has low probability or that outcome never happens. You don't care. You want it to converge to x for all probability. So it's too strict of a condition. So what we do is we lose the condition a little bit. And now you have xn, a sequence of random variables. You say that xn converges almost surely to a random variable x if probability of set of omegas such that x omega converges to omega is equal to 1. So how did we loosen that property is, so you just want convergence in those outcomes whose probability is 1. So what is this? This is a set of all the outcomes where you have convergence. Now, if the set of outcomes has a probability of 1, then you say that the sequence of xn converges to x almost surely. So I'll show you some examples later. Okay, maybe I can give it now only. So one example is, suppose you have a random variable xn. Okay, so yeah, before giving the example, I'll give the probability triplet, the outcome, the event space, and the probability. So this is, so let the outcome be random number from 0 to 1. Event space, the Borel set of 0, 1. I have not explained this, but this is a sigma algebra on the set 0 and 1. You know what a sigma algebra is, so it's just a sigma algebra on the set 0 and 1. It's basically contains all the sets, all the open subsets of this set, and also it contains uh, all the other sets such that this forms sigma algebra. That whole collection is known as the Borel set. Don't need to go deep into it. And we have the Lebesgue measure. The Lebesgue measure is just the uh, interval length. So, so what is the probability that so this probability measure is given by uh, your outcome could be your omega could be anything between 0 and 1. So what is the probability that omega belongs to a comma b? This is b minus c. The interval length for a and b being between 0 and 1. So that is the Lebesgue measure. So yeah, this is the probability interpolate. And then you have xn equal to the random variable n when omega belongs to 0 comma 1 by n. 0 otherwise. But this is clear. So when you have an outcome which belongs between 0 and 1 by n, then the random variable takes the value of n. If it does not belongs to 0 and 1 by n, then it takes 0. The x n. So x1, the random variable x1. Okay, so what this means is, so x1, sorry, x1 is always 1 because 1 by 1 is 1 and all the omegas will belongs to 0 and 1. So x1 is 1 almost always with probability 1. X2 is 2 with probability 1 by 2 because you have 0 and 1 by 2 and 0 with probability 1 by 2. X3 has 3 with probability 1 by 3 and 0 with probability 2 by 3. So on. Xn has probability n with probability 1 by n, 0 with probability 1 minus 1 by n. And this keeps on going. As you see, the probability that xn is equal to n keeps on decreasing as n increases. So you can say that you can intuitively see that this random variable is converging to a random variable which is always 0. X which is always 0 with probability 1. So in this case, what happens is, so you have this sequence of random variables. Yeah, this is an example of almost sure convergence. We'll show how this is almost sure, but intuitively you can see that as you increase n, as you increase n, you're converging somewhere to 0. But this is not how you show almost sure convergence. We'll see that a bit later. Before that, I'll state all the notation, no, all the notions of convergence. So the next one is convergence in probability. Okay, so we say that you have a sequence. We say that a sequence xn converges in probability to a random variable x if limit n tends to infinity, probability mod xn minus x greater than epsilon equal to 0. So what this is telling is you take the probabilities of this event for each n, and you see what happens. This is for all epsilon greater than 0, and you see that what happens to this event for all. So basically you have a sequence of probabilities. You generate a sequence of probabilities and you see whether the sequence of probabilities converge to 0 in your notion of convergence of real numbers, because probabilities are just numbers. So yeah, in the previous one, so let me write it down clearly. So what you have is almost sure convergence. You collect all omegas where xn converges to x and call this as the event A, the collection of all the omegas where convergence happens. And if the probability of A equal to 1, then it means that it is almost sure convergence. You have convergence in probability. So what you do is you you design an event of this form for each n. So a and epsilon is an event of this form. You find the probabilities of this event. Now, if the probabilities of this event converge to 0, then you can say that xn converges to x in probability. These both intuitively feel the same, but they're different. And we'll see that this is a more stronger condition and this is a more weaker condition. Um, Next we have convergence in R mean. If you guys have any doubt, you can ask me whenever you want. So xn again,
Sir,
yeah,
can you hear me?
yeah, I can hear you.
Yeah. So almost sure is you collect all those omega, and the set of all collection of omega is said to be A, right, sir?
Yeah. You collect all the
Then
you
yeah, yes,
collect
sir.
you collect all the omegas where xn
Mm.
converges to x.
Okay, then how could we say probability of the set A is equal to 1?
That if probability of set A equal to 1, then that implies that xn converges to almost sure x.
No,
How do
what
you
I'm asking is how can I find out the probability of all the elements in A?
yeah, that is uh, 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 like I'll give you example how to find the probability of all the sets in A.
Okay, sir. Okay, sir. Thank
Yeah, so this is just like uh, what to do. So
you. Okay,
you
okay, sir.
need, this is the, like what I'm saying is how do you show that if xn converges to x almost surely, this is the method that you need to do. Now how do you
Mm-hmm.
calculate that? I'll give some examples.
Okay, sir. Thank you.
I'll do that. Okay, convergence in Rth mean. You have a sequence of random variables xn. Now you say that xn converges in Rth mean to x if limit n tends to infinity, expectation mod xn minus xr equal to 0. If this condition is set, so this is basically saying that the expectation of the um, mean squared, it's not mean squared because it's a rth mean. So the expectation of uh, some mean expectations is going to 0. So here again, you take the random variables, you calculate some terms which are real numbers, and you check whether they converge in this in the notion of real number convergence, not in random convergence. Yeah. Next, the weakest of them all is definition, convergence and distribution. So xn converges in distribution to x if limit n tends to infinity fxn x equal to fxx for all x belongs to R, where fx is continuous. So this is also known as weak convergence. This is the weakest of all convergences. So yeah, coming back to this example for almost sure. Okay, so yeah, your doubt that you had. So I'll try to show that this example um, is almost sure. So there we'll try to collect all the omegas and find the probability of the omega. Okay, so basically I'll write it down again. Example. Uh, you have xn equal to n if omega belongs to 0, comma 1 by n and 0 otherwise. So this can be written as xn equal to n with probability 1 by n, 0 with probability 1 minus 1 by n. This we have done before. So now what I want you to see is when omega is not equal to 0. So what does this mean is omega belongs to 0, comma 1. So open 0, closed 1. Yeah. Then you can see that limit, sorry, uh, limit n tends to infinity, xn omega equal to 0. Okay, so to illustrate this, what I'll say is take omega equal to zero point 0.5. If omega equal to zero point 0.5, then the sequence that you get is x1 would be 1, x2 would be 2, x3 would be 0, and so on. It will go on till 0. So any omega you take which is not 0. So suppose you take an omega which is very small, omega equal to 0.01. Then this is basically 1 by 100. So you go till 100. So x1 equal to 1, x2 equal to 2, and so on. X100, it will be 100, but after that it will be all zeros. So for any omega you give, which is not equal to 0, this sequence will always converge to 0, always converge to 0. That is what I've written here. But when uh, when omega equal to 0, then we can see that limit n tends to infinity xn omega equal to plus infinity. Because 0 will be there for any n you give me, 0 will always be in the omega. So if omega is 0, so the sequence would just be a series of natural numbers, 1, 2, 3, and so on till infinity. So this will shoot up to infinity. So this will shoot up to infinity. Now you have the events omega belongs to 0 and 0 to 1, where the limit converges to 0. And you need to just find the probability of this event. So probability of 0, comma 1 is 1. And which is the length of the interval. The length of the interval is 1, so it's 1. And now you have shown that uh, xn converges to 0 almost surely. Uh, is this understood? Like, this is how you do it. So you collect all the events where the convergence happens, and then you find the probability of the convergence based on the probability space that you have given. That is given to you. The probability space is given to you, and sequence of random variables are given. Using those properties, you try to show whether it converges almost surely or not. Is this clear?
Yes, yes, sir.
Okay. There are actually like your point of question is actually good. Like this is very basic example of how do I collect omegas and find the probabilities. But there are actually many other ways of how to show probabilities almost sure. We'll cover some of them in today's class. We'll go through them, but for that I'm just developing. I'm going slowly. So this is the first how to show that this is an almost sure convergence. And also, do you understand that this example that I've given, it's not pointwise convergence. Could you see that? Because for all omegas, it is not converging to zero. Only for some omegas, it is converging to zero. But the probability for those set of omegas is one, hence it's almost sure convergence, but it's not pointwise convergence. Is that clear here?
Yeah, I got it, sir.
Okay. Okay. Next is so yeah. So now my question to you is, um, would this converge in probability? The same example, would this converge in probability? Okay, I'll show what in probability means. Yeah, in probability. Yeah, this example, you can take some time, no problem. Okay, okay, I'll do the improbability part also. So uh, take some epsilon greater than zero. It doesn't matter what epsilon is. It's fix some epsilon greater than zero. Hello, I'm still audible. Okay. Fix some epsilon which is greater than zero. Now what you do is you take limit n tends to infinity probability of mod xn, because you're trying to show that converges to zero, is greater than epsilon. Now, okay, this uh, is basically the probability that xn equal to n. Is that clear? The event that xn is greater than epsilon is equivalent to the event that xn equal to n. Is that point clear?
Yes, sir.
Uh, it is clear, right? The probability that the event xn is greater than epsilon is equal to the event xn equal to n, because xn can only take two values. It is either n or zero. So
Yes.
so xn is greater than something positive ultimately implies that it is greater than zero. If it is greater than zero,
Yeah.
it should be n because it can't take any other value.
This is
Yeah, you're correct. Yeah. So now we know the probability of this is xn equal to n is 1 by n. You know that the limit of this sequence is zero. So you can conclude that xn converges to zero in probability. Is that
yes,
clear?
sir.
Okay.
Okay, yes, yes. Sir, but one more doubt.
Uh-huh.
Probability of xn equal to n, how could we say that 1 by n? Because in before the definition, you took the limit 0 to 1 by n. That's why. Yeah, this xn equal to
Yes, yes.
n,
With
where 1 by
probability 1
n.
by n. Yes, I took while defining the sequence of, you're absolutely correct. I took the sequence of random variables xn. I defined them such that
Yeah,
if omega
omega
belongs to 0,
0,
0
comma 1 by
1
n.
by n, it is n. Yes.
So yeah, I got it, sir.
Okay. The probability measure is the interval, the length of the interval. It could be. Yeah, you're
Okay.
correct. You're correct. You're correct in that. Confusion, no? But yeah, so now you see that this sequence. So these sequence of random variables, if I give you a sequence of random variables, converges to zero almost surely, also converges to zero in probability. You have had some basic ideas of how to show convergence of in almost surely and in probability. Okay, so let us do two more. We'll do one in Rth mean. We'll do square mean and so, okay, let me write it down. I think I'll write this down every time so that it will be clear. Xn equal to n with probability n, 0 with probability 1 minus 1 by n. So this is your basic example. Like this is the example that we're trying to show. Okay, so we are doing second mean convergence, two mean convergence, not second mean, two mean convergence, uh, second mean convergence. Okay, yeah. So what I want you to calculate is limit n tends to infinity expectation mod xn square. Okay, what does this term for this function for this turn out? Could you calculate the expectation? Limit n tends to infinity. This will be expectation of xn square. So xn is this, mod xn would also be n because n is always positive with probability n, 0 with probability 1 minus 1. Nothing changes here. Mod xn square would be n square with probability n, 0. 0 square is 0, 1 minus 1. So the expectation of this random variable would be n square. Okay, with probability 1 by n. Sorry, probability 1 by n. N square into 1 by n plus 0 into 1 minus 1 by n. So this is the expectation of mod xn square. This will be n. So n limit n times infinity is infinity. So this does not converge in rth mean convergence. So this example, this does not converge second mean convergence to 0. Does not converge to 0. I hope this is also clear. Why it doesn't converge? Okay. Am I audible, right? Hello.
Yeah, yes, sir. Sir, shall I ask you one question? Actually, which is a silly question, but I wanted to
No,
know.
no, no, it's okay, fine. Yeah, go ahead, please.
Why should we need to find out the expectation of some xn like that? What does it mean by finding expectation here?
Finding expectation here. Okay, so you have a random, you have many random. Okay, so you want the intuition behind. Um, okay, so let me reiterate the question properly. So you want the intuition behind why do I need a convergence in rth mean? Right. So basically, all the convergence before this were in convergence in probability and convergence in uh, you collect the events, you find the probability, or you find the probability and show that the probability converges to 0, and so on. Okay, in rth mean, what you want to do is you have many random variables. What you do is you subtract. So you subtract the sequence random variables with um, the random variable which you want to converge, and you see that when you subtract this, you get a new random variable. So this whole thing is a new random variable. Now, what you want to say is, if when you say that something is converging to something, so it is actually going towards it, or it is equal to that. So when you can either say xn minus x is 0 always. If it is always, then it is pointwise convergence. In probability, you can say that, okay, I want to find the probability of all these events there and show that it is 0. Now, expectation of this means it will not always converge, but um, the most number of times it will converge. It's not even, you can say it's in a sense not weaker than probability, but uh, it's like the most expected thing that could happen is xn would converge to x. The most expected thing that could happen is xn would converge to x. That is what this convergence intuitively means. It's not weaker to probability, if that is what was the question, but it's just like uh, instead of calculating probabilities, you calculate the expectations and show that xn minus x random variable is 0. So if you want to say that something is different to something, you subtract those two and say, so if you have two numbers, 2 and 5, you subtract those two and say that, okay, if it is positive number, then this is greater than this. If negative number, then this is less than this. If it is 0, then they both are equal. So the same thing we are trying to do here is, as n tends to infinity, does xn minus x in expectation go to 0? Does it answer your question?
Yeah, little bit I have doubt, but yeah, now it's okay.
Okay,
If
so
I'm not clear until this class end, I'll ask you again.
okay, sure. Okay. So next is the implication diagram. So uh, if you have pointwise convergence, it always implies that you have almost sure convergence, because pointwise convergence means any outcome you take, xn, the sequence converges to x. Almost sure means you just take only, it converges only in those events whose probability is 1. It doesn't converge in those events whose probability is 0. So if you have a pointwise convergence sequence, then that implies that you have an almost sure convergence sequence. But the other way around is not true. We have just seen an example for that. If it is almost sure convergence, then it implies that it is improbability convergence. We have seen this implication. We have seen an example for this implication. We'll see a counter example for the other way around. I have not proved that almost sure convergence implies improbability. I've just given an example where you have seen that it is almost sure convergence and also it is improbability convergence. Improbability convergence implies convergent distribution. Rth mean implies improbability. Rth mean also implies Sth mean, where R is greater than S. So this is the implication diagram. Okay, so first theorem of today's class. So we'll prove if you have a sequence of random variables which converges in the rth mean to x, this implies xn converges to improbability in x. Okay, so to show improbability, convergence in probability, what you need to show is limit n tends to infinity, probability of mod xn minus x greater than epsilon. This should go to 0, right? Okay, so whenever you see this kind of inequalities in probability events, you can directly apply inequalities which were discussed in the last class. So you know Markov inequality. So let us apply the Markov inequality here. This is expectation of mod xn minus x. So, okay, before applying Markov inequality, uh, what I'm doing is if this happens, then this is equal to limit x probability mod xn minus x whole power r greater than epsilon r. For r greater than 0, r3 is greater than 0. Now you apply the Markov inequality less than or equal to limit n tends to infinity expectation mod xn minus x r by epsilon r. Now you can see that this is equal to 0. So you have shown that limit of probabilities is less than or equal to 0. If limit of probabilities is less than or equal to 0, that implies that limit of probabilities is equal to 0 because probabilities can't go to negative. So you have just shown that limit n tends to infinity, probability mod xn minus x greater than epsilon equal to 0, which implies xn in probability to x. This step is from xn rth mean. Limit n tends to infinity, expectation of xn minus 1 is 0. So given this, we have shown that xn converges to x in probability. You don't need to prove this. So if you can prove that something converges in rth mean, uh, then it converges in probability. But the other way around is not true. Can you give an example of the other way around? Like why the uh, xn, like given counter example, why xn converges in probability to x does not imply that xn converges to x in rth mean. So this is the example. The example that we did, it converged in probability to 0, but it didn't converge in second mean to 0. So this is a counter example which says that you can have convergence in probability, but not in rth mean sense. So basically this implication diagram does not go this way. So it does not go the other way. So improbability does not imply rth mean. Rth mean implies improbability. I hope that is also clear. Um, okay. Okay, so I have one more theorem. Okay, so this theorem is, if for all epsilon greater than 0, summation n probability of an epsilon is less than infinity, then xn almost all x, where an epsilon is set of omega such that mod xn minus x omega greater than epsilon. Hmm. So what this is saying is, this is an event, right? This event says collect all the omegas where xn does not converge to x. Now, if the sum of the probabilities of these events is less than infinity, then xn almost surely converges to x. Uh, do you understand why this is true? Like the intuition behind it. Okay, so for this, I think we need to go back uh, to Borel Kant. Yeah. So, hmm. So when we have a sum of probability of events, sequence of events less than infinity, then almost surely finitely many AIs will occur. So what does this mean is, occurrence of AI is finite. So occurrence of infinitely many AIs is zero, but finitely many AIs only will occur. So this event will occur only finitely many times. So now this event is set of omegas where x does not converge. This will occur finitely many number of times. So that means there will exist an capital N in the natural numbers, after which this event will not occur. So this event will not occur. Uh, so what intuitively says is, the probability of this event is zero, because uh, these are the set of all omegas where convergence doesn't happen, and they'll happen only finitely many number of times. The limit of the random variable will mostly converge. That is the intuition behind this theorem. Uh, the proof is actually a long proof. I think I'll not be able to complete in this class, but yeah, we'll be using this. So as your question, how do I find the probability of the probability of the uh, uh, omegas that I've collected and show that that is equal to 1. Instead of collecting the probabilities of events, collecting the events and showing that it is 1, you can find where it does not converge and show that that probability is 0. Or you can also make a, set of this sort and show that the sum is less than infinity, which then implies that xn almost surely reaches x. So using this theorem, we'll try to solve problem. So exercise. Let Q be uniformly distributed between 0 and 1. So U is a number which is uniformly distributed to 0 and 1. Let Xn be minus 1 whole power n U by n. Okay, show that. So the first question is show that Xn converges to 0 almost surely. Okay, so we'll try to show this solution. We'll use the above theorem. I will show the implication of how the above theorem works. Okay, so now you're defining A and epsilon as omega belongs to omega such that, okay, set of. So you're defining this set omega, omega such that mod xn is greater than epsilon. So what you want to show is probability of A and epsilon infinitely often equal to 0. If this you're able to show, which is basically saying that summation of ans is less than infinity, then you can say that xn is almost surely converging to x. So infinitely often, while deriving the uh, Borel-Kant lemma, I've showed that infinitely often means union of n belongs to n. Intersection of this you have to show. You have to show n m greater than or equal to n set of omega such that mod xn omega less epsilon. Okay, just 1 minute. Sorry. So what we are trying to show is uh, this is for infinitely many of infinitely many infinitely often is intersection of union. But what I'm trying to show is I'll take the complement and try to show that it is one. Yeah, that is what I'm trying to. Sorry. So instead of showing this, I'll show that. So what this is intersection of union. Intersection of union of set of A n epsilon equal to 0. Uh, what I'll show is probability of the complement of this is 1. This complement would be uh, union intersection A and epsilon complement equal to 1. I'll try to show this. So this will imply this. Okay, is this clear? Like, am I making sense or completely you're not understanding?
Yes, sir. Yes, I could understand this.
Okay, okay. Thank you. Sorry for the confusion. I got confused what I was trying to do. Okay. Yeah, union intersection. So the complement of A n complement would be just the less than or equal to epsilon. This. Yeah, we're trying to show that this is equal. The probability of this is equal to 1. Okay, so yeah. So now this I can write as probability of union intersection omega such that u of omega is less than or equal to m epsilon. This is m n because this over m. Is this clear? So what I did here was I replaced xn equal to minus 1 whole power n u by n. So mod xn is equal to u by n. Mod xm is equal to u by m. So here I have xm. So the m goes that side. It's um less than or equal to n, which is equal to uh, probability of union omega such that u omega is less than or equal to n epsilon. Okay, here I have m greater than or equal to n, and this is n belongs to all natural numbers. Here n belongs to all natural numbers. So u omega is less than m epsilon. This is an intersection. So all these events would be satisfied. So intersection of u less than m epsilon. So if it is less than the least, you're done. The least is n. So instead of writing intersection of all those, you can just write intersection of u less than n epsilon. So it is something like a uh, increasing set, and the intersect increasing sequence of sets, and the intersection is the smallest set. The smallest set being u less than n epsilon. Is that okay? Do I make sense? How did I go from this step to this step? That you have understood, right?
Yes, sir.
Okay. Uh, then basically this is just the whole sample space, and this is one, because un is less than n epsilon. This is for all epsilon greater than 0, and uh, n is a natural number, it could be a natural number, so it's less than, so you will take all values between 0 and 1. So yeah, this is the whole sample space, and you get this equal to 1. So probability of this equal to 1 implies that probability of a and epsilon infinitely often equal to 0. And from this theorem, you can say that probability of a and epsilon infinitely often equal to 0 implies that xn is almost sure converging to x. Okay, so this is how you also can show almost sure convergence. So yeah, so the proof for this theorem, if you want, I can do a separate class. Maybe not next class, but some other time I can do the proof for this. It'll, yeah, this proof. But for now, take it for granted that uh, if you can generate these types of events and show that these events are not infinitely often, don't occur infinitely often, then xn converges almost surely to x. Okay. The next question, the same question here is uh, B. Show that xn converges in mean squared sets. Okay, B. So basically, you're trying to find expectation of mod xn square, which is equal to expectation of u square by n square, which is equal to 1 by n square into 1 by 3, which implies limit n tends to infinity expectation xn square equal to 0. Therefore, xn converges to mean squared in 0. So mean squared is the second mean convergence. Okay, yeah. So this is also clear. Okay, so yeah, this is about convergence. So I have half an hour more left. So you have any doubt on convergence still yet, or you can ask me, because I'll be going to limit theorems now, like central limit theorem, strong law of large numbers theorem, and others. I think your doubt on the expectation, like why this notion of convergence is required is not yet this cleared. I think maybe I'll get back to it later. So your question was, um, what is the intuition behind having the convergence in Rth mean?
Yeah, yes, sir. Yes.
I'll so I don't think like there's an intuition, like historically what they would like so this first started with working with pointwise convergence. Then they felt that pointwise convergence is too strong. We'll not be able to derive many new things like some other convergences. So they loosened it up by almost sure convergence. Then they were like, no, almost sure convergence is also very strong. So let's loosen it up with convergence and probability. And then since now we're working with probabilities, you can also work with expectations. Since expectations are also real numbers. So you're basically looking at limit of sequence of real numbers for the random variable. So given a sequence of random variable, so given a sequence of random variables, what you're converting this into is a sequence of means. And then you're saying, how does the mean of this compare to the mean of the convergence thing that I'm about to say? So it's not exactly that, but the intuition is that. So instead of looking at randomness, I'm looking at real numbers, which I can work with very easily. Real numbers convergence, I know. So what all things that I can extract given a random variable? I can extract the mean out. So, okay, let me extract the mean out and say how far the sequence of means are from each other. So now I create a new sequence, mu1 minus mu1, mu2.
My
Yeah.
question is not only in orth mean, okay. What my question
Mhm.
is, why should we need, why should we find out the expectation in whatever we need? That's it.
Oh, why do we need to find the expectation? So
Yeah,
expectation.
what's the
mm,
intention behind the
mm,
expectation, finding
So
expectation? That's my question.
okay, so finding expectation, basically what you're doing is you're eliminating the randomness. Once you're given a random variable, so xn minus x is a random variable. It's still random. It is a random variable with y. It has a
Yeah.
distribution and it has all. So then again, you need to show any convergence of y to 0. You need to again fall back to randomness in convergence. So now, given this random variable, I want convergence in a sense where I can where I'm very comfortable with, such as real numbers. So instead of I want to eliminate the randomness. So what I do is, okay, what is the most expected thing that xn minus x will give? So I calculate I take the expectation of it. It gives the most expected thing. Okay, in most expected thing, does it converge? That is what I'm trying to show. So I'm taking something which is random. Using expectation, I'm converting it into real numbers, just numbers. Because given a random variable, that expectation would just be a number. So here I have a sequence of numbers. If it converges in expectation, then I say that, uh, yeah, if this real number sequence converges to 0, then I say that my random variables, the means of the random variables converge at certain rate. That rate is actually depending on R, but at what rate it converges, that is on R. So yeah, that thing. But why expectation is because I want to convert randomness to real numbers so that it is easy to work with. But I'll keep this question in mind and I'll get back to you later also. Why
Okay.
expectation?
Okay. Okay. So,
Okay. So next, just one. Sorry. Um, okay. So next are the limit theorems. So what I'll do is I'll state all the limit theorems that I have. Proving each and every one of them would be like very difficult. Proving some are very easy, but I don't think I have time for that. So I have uh, a question on uh, limit theorem. So I'll focus on solving that question for limits theorem. That will give you an intuition, but I'll just state the theorems. All the theorems I'll state what all theorems we have. So here also you'll find that in the limit theorems also you'll find the notion of weakness and strongness. So this weakness and strongness come from the same convergence notions that we stated above. So okay, so let me state the first. The first is L2 weak law of large numbers. Okay. So Xn be a sequence of uncorrelated RVs with expectation of Xn equal to mu and variance of Xn equal to sigma square. Then sample mean Xn, which is given by summation I equal to 1 to n xi, converges to mu in probability. I hope you see that this is also a random variable because x's are random. It converges to a deterministic number mu. In probability, I hope you understand what that means. So the limit of probabilities of uh, the set where this does not converge to mu is equal to 0. Uh, L1 weak law of large numbers. Okay, so you have Xn sequence of uncorrelated. No, not uncorrelated. Sequence of IID random variables with expectation of Xn equal to mu. Then sample mean 1 by n summation xi I equal to 1 to n in probability to mu. So as you can see from the above theorem to the below theorem, what we have is here you need bounded variance. Here you don't need a bounded variance. So even if the variance is unbounded, what this law is saying is that it will converge in probability 3. So these are basically the limit theorems are basically this strong law of large numbers. So all the law of large numbers are basically saying the same thing, that the sample mean will converge to the mu, but what is the convergence that changes. So all the weak laws are converges in probability. All the strong laws are almost sure convergence. I hope you understand the difference. And these L1, L2 are what are the assumptions that you need to prove that. So yeah. Uh, but in general, the strongest law says that uh, you have a sequence of random variables uh, whose means are bounded, then the sample mean converges to the mean. That's it, you're done. Like that goes through, but proving that is very difficult. So what people did was they proved something which is weaker. So they assumed some assumptions, then they showed that it's in probability. Then they loosen that assumptions and try to show, but the strongest one always holds. So it holds no matter what, the strongest one holds. But these are the variations of the limit theorems. Then L1 weak of large numbers. Then we have L4 strong law of large numbers. Here you have Xn independent random variables, need not be identical, with bounded fourth central moment, that is sup of expectation Xn minus expectation Xn whole power 4 is less than or equal to b is strictly less than infinity. So this is known as uniformly bounded. So if this happens for all the random variables, then the sample mean converges to mu almost sure. So from weak to strong, improbability becomes almost surely. This L2 L2 weak just states which central moments, which moments you use as assumptions. So L2 you use the mean and variance. L1 you just use the mean. But then here they're uncorrelated. In L1 you need independent. In L4 strong law of large numbers, you need the expectations to be uniformly bounded. And if they're uniformly bounded, the fourth moment, then it's almost surely bounded. I'll state the most strongest of all, which is the L1 strong law of large numbers. This is the one that we'll be using regularly, the L1 strong law of large numbers. So if you have a sequence Xn with uniformly bounded absolute means, that is supremum of expectation of absolute means. So expectation of mod Xn is less than B is less than infinity, same, uniformly bounded. If this happens, then Xn converges to mu almost surely. So when people say strong law of large numbers, they mean this. This is the strong law of largest numbers. These are more weaker conditions, but if this satisfies, then you can see that all the rest of them also satisfies. Then the central limit theorem. Xn IID sequence of RB. IID is very important. Expectation of Xn equal to mu and variance of Xn equal to sigma square for all n. Then Sn, I'm defining it as sum of I equal to 1 to n. Then central limit theorem says that n mu by sigma root n. This random variable converges to y. Now y is a random variable whose distribution is 0, 1. So the distributions of y and this are the same. So this has a distribution of normal 0, 1. This is what it says. So basically we'll be using these two laws. So the strong law of large numbers says that if you have a sequence of random variables and the mean is uniformly bound and the absolute mean is uniformly bounded, which means this, then the sample mean converges to mu almost surely. Central limit says that if you have a sequence of random variables which are IID with uh, finite mean and finite variance, then the sample mean converges to a random variable whose distribution is Gaussian. Or you can normalize it by subtracting with n minus v and dividing by sigma by root n, and you can say that converges to normal distribution. Is that clear? These two limit laws. Okay, I'll not be doing the proof, so I'll go to the exercise. Okay. Okay. Consider a sequence of IID Bernoulli random variables Xn with parameter P. Okay. Now I'm defining Sn equal to summation I equal to 1 to n xi using SLN and SLT. What can be stated? Okay, so first solution. Okay, first using SLN. What can you state using SLN? So you have a sequence, you know the sequence. So for to so the what the sample mean is given by Sn by n. This is the sample mean, right? Yeah. What is the assumption that you need to show that this converges to something? For strong law of large numbers, you need to show that the absolute value of each number in the sequence is bounded, uniformly bounded. So as you know that xn's are Bernoulli, so you know that expectation of mod xn is equal to p. Okay, Bernoulli is 1 with probability p and 0 with probability 1 minus p. Mod xn also will have 1 with probability p, 0 with probability 1 minus p. Expectation of mod xn, you will have 1 into p plus 0 into 1 minus p. So this is less than infinity. This is sure. So you have uniformly bound shown the uniformly boundedness of this. So supremum of expectation of mod xn is less than or equal to p is less than infinity. Because for all it is p, so the supremum of all would be less than p. It doesn't matter. Sorry, supremum of all this is equal to p, because all are p, so is equal to p, which is less than infinity. So we've shown uniform boundedness. This implies that Sn by n converges to p almost surely. Is that clear? Like that is clear. Uh, then central limit theorem, what can you say? Xn's are IID with mean p and variance p into 1 minus p. So from central limit theorem, you can say that Si minus np by root p into 1 minus p into n in distribution converges to a random variable y whose distribution is the normal zero. This is what you can state from central limit theorem. Okay. These both are clear, right? Okay. So one more thing I'll do is, okay, I'll try to find limiting distributions. Okay. So Sn, again, I'm defining it as I equal to 1 to n xin. But xin is uh, distributed Bernoulli lambda by n for 1 less than equal to y less than or equal to n. So you have Bernoulli distribution. So now we want to show using central limit theorem or something like what is the limiting distribution of this. So I don't think you need to use central limit theorem here, but yeah, we'll see. So probability of Sn equal to k. This example I'll talk when I'm doing Poisson distributions, Poisson process. Sorry. Yeah, this doesn't use distribution. Okay. Okay. Yeah, sorry. Next exercise 2. A town starts a mosquito control program and the RV Zn is the number of mosquitoes at end of nth year. N is your 0, 1 natural numbers. Xn is the growth rate of mosquitoes. So what it means is Zn equal to Xn into Zn minus 1. Assume that these Xn's are IID. These are IID. With probability of X equal to 2 equal to xn equal to 2 is equal to 1 by 2. Probability of xn equal to half equal to 1 by 4. Probability of xn equal to 1 by 4 is equal to 1 by 4. Z0 is known and positive. So the first year there are some positive number of mosquitoes. Uh, so what we want to find is we want to find expectation of Zn and limit n tends to infinity expectation of Zn. We want to find this, and using this we want to tell something about how successful the mosquito control program is. So yeah, we know that Zn equal to xn into Zn minus 1. But Zn minus 1 is equal to xn minus 1 into Zn minus 2. So this will go on till Z0. So this is basically product of n xis into Z0. Now, given that x's are IID, expectation just productifies out. So the expectation of Zn equal to expectation of x1 whole power n into Z0. Okay, from here to here, I've used independence identically distributed. What all the things, the independence productifies out the expectation. The identical all have the same expectation, so whole power n into Zn. Z0 is known already, so it's just a number. It's not a random variable. Okay, so now I want to find expectation of x1. Expectation of x1 is equal to 2 into 1 by 2 plus 1 by 2 into 1 by 4 plus 1 by 4 into 1 by 4, which is 16, 19, 19 by 16. Yeah. So you have expectation of Zn equal to 19 by 16 whole power n Z0 and limit expectation Zn equal to infinity. This is positive and greater than 0. Because if this would be 0, then expectation of xn would be 0. There would nothing to grow. So using these two, we can't say anything about how successful the like this does not imply anything on what the limit n tends to infinity Zn converges to. This says that the expectation of Zn is infinity, but we can't say anything about uh, like how successful the mosquito control program was. Even we can't say anything about expectation of limit Zn. This also we're not able to say from this. So to say something successful about the mosquito control program, uh, we will try to find Wn, which is log 2 xn, and we'll find expectation of Wn and expectation of log Zn by Z0. From this, we'll show that log Zn by Z0 converges to some number. And what this means that if this number is less than 1, if this number is negative, then Zn by Z0 is less than 1. If Zn by Z0 is less than 1, then you can see that the number of mosquitoes each year is decreasing. And since it's decreasing, you see that how much effective that the mosquito control program is. Just directly calculating expectation of this, you can't say anything. So you need to do this. For this, we'll use center limit theorem. Yeah, center limit theorem. Sorry, strong law of large numbers. Strong law of large numbers. Okay, so first we'll calculate what expectation of Wn is. Wn is equal to expectation of log to xn, which is half log 2 plus e raised to 1/4 log 1 by 2 plus 1/4 log 1 by 4. This is minus 1 by 4. So now we have log Zn by Z0. This is summation. So Zn I can write as product of um, x1 to xn, z0. Z0, Z0 cancels. I have log product of x1 to xn. Log product of x1 to xn, I can write as summation of log of xi's I equal to 1 to n, which is equal to summation I equal to 1 to n wi. Uh, yeah. So from here you can see that 1 by n log Zn by Z0 to the base 2 almost surely converges to minus 1 by 4, the expectation of Wn. This is based on strong law of large numbers. So as you can see that this almost surely converges to minus 1 by 4. So this converges to a negative number. The log of something converges to a negative number. So Zn by Z0 is less than 1. So Zn by Z0 being less than 1, what it says is Zn keeps on decreasing as n increases. So from this you are able to conclude that the mosquito control program is actually working. So yeah. So what this question tries to answer is sometimes when directly you can't find uh, how good a system is, you can manipulate it using logs and uh, using SLN and CLT, you can try to show the convergence of these logs to a negative number or something, and then claim that a system is working better or not. Yeah, I think I'll end my class for today. Do you have any doubts you can ask? Let's stop the recording. Yeah.